audio.
Sure. So once again, also with audio now, hello everyone. Thanks for coming to USC to attend L4DC in News this year. I don't want to take too much time because we lost a bit already. This is the first tutorial in the morning on bridging control and learning for safe and scalable autonomy, a tour through the lens of robotics. And I'll just hand over to Aaron to kick it off. Thank you so much.
Welcome, everyone. It's nice to see a big crowd. So I'm also going to jump right in. I'll try to make up a little time. But I think this is a really fitting tutorial. And actually, our computer crash is even fitting for what we're going to talk about today on this sort of inherent fragility of physical systems and how do we understand that and what does that mean for learning and control. So first, thank the organizers. Everyone on here did a lot of work. I did the least amount of work of everybody on this slide. So I just want to thank everyone for everything they did. So let me open with a mood picture. And the mood picture is robots are here. As everyone knows, you see YouTube videos all the time. It's really amazing what's happened in the last couple of years with humanoid robots. It's really incredible. We went from, maybe 4 years ago, there was like 1 or 2 humanoid robots out there. And now we have, endless number of startups in humanoid robots. And the videos that are being produced and the motions that are being produced are really impressive. I think the motions to me are the most impressive part, the top videos, let's say. What we can do with humanoids now from a dynamic locomotion perspective is honestly jaw-dropping. We used to be happy when we could get a robot to walk in 3D. That was a huge achievement, and now they're like doing backflips and kicking. It's pretty cool. Of course, the bottom is kind of the more marketing side of this whole endeavor. And that's also very impressive, but there's definitely a blurring between fact and fiction, let's say, right now in a lot of these videos. What I mean is the one thing these all have in common is there's humans behind them right now, right? Like none of this is autonomous. So all the videos you see, all the backflipping videos you see, this kind of shows this technology. Of course, the methodology more transparently is it's all like mocap human data based. Right? So a human performs an action, they retarget those trajectories, they train an RL to mimic those trajectories essentially, and they pop it on the robot. So it's all completely, let's say, open loop trajectory playback, right? All the autonomous stuff you saw, meaning the cool videos of robots in the home doing things, that's all like teleop, essentially, right? There's some VLAs that are trained up now for specific tasks, but by and large, all of the large-scale stuff you see is this teleop, and this is a video of me doing it in my lab on the G1. This was like a year ago, but it shows that this stuff is pretty easy to stand up in a stack. And it looks really cool if you don't see the person behind the curtain, right? It kind of feels a little Wizard of Oz. If you ignore the person behind the curtain, it looks like this robot is intelligent. And when people see this stuff online and see the videos of a robot like picking up and putting away dishes and things, right? It's usually a teleoperator, and unless it's autonomous. If it's autonomous, it's very slow, very error prone, right? So this is the reality of where we're at. And this is made really clear by this video, which I don't even like showing, but I'm going to show it anyways. It's painful for me to watch. And what's happening here, of course, is that there's open loop trajectories. They're playing back on the humanoid, and a kid stands in front of where the humanoid's going. It has no autonomy, no perception of the environment. It's just like going and doing its little dance. And of course, it kicks a kid in the middle. I'm going to stop that. So thank you. It's hard for me to watch. Also, there should not be humanoid robots around kids like this in public. This is just like a bad idea, and I don't know why people are doing it. Somebody's going to get really hurt very quick, very bad, and very fast. So the point is, if we put AI on robots, and I hate the word AI, but I'm going to use it anyways as like an umbrella term. If we put like software on robots that we don't understand, bad things are going to happen. And right now, they're small little examples. There's going to be really big examples soon, and it's going to be like a day of reckoning for all of these robot companies when something really bad happens. At least that's my claim. We saw it with autonomous cars. We're going to see it with humanoids. So what does that mean? What's happening at a broad level? I really like this kind of plot, this overview of where we're at right now. Think about learning and performance as being tightly coupled. So learning learns in optimal, right? That's effectively what it does. It does it from data. It does it in unstructured ways. It can do it from simulators. And in the end, it gives you really impressive behaviors that are performance-based. But performance by itself is not sufficient, right? So here you see, this is a figure video I think it's teleoperated, and what you see at the end of the video is there's a kid standing right by the robot, which terrifies me too, to be honest. It's cool that it can do this, even teleoperated. There's some autonomous versions of this as well, but the reality is that without understanding the safety case, for example, without understanding how to make sure that if there's a kid next to the robot won't flail its arm out and smack the kid, right? We're not going to be able to deploy these robots. So this is just like a heading. It's not so much to blame Figure. Nothing's happened. Figure has not made a mistake yet, just to be clear. But without thinking about safety and reliability and robustness, there will be failures. So I contrast this with kind of the current state of the art of safely deployable robots. I mean robots that are safety certified to actually be deployed autonomously around people in the field. And the state of the art is really Proteus right now. So this is an Amazon robot. There's many of these. They have over 1 million robots in the field right now. There's a safety stack on this robot. It's safety certified, and it can be around people autonomously using perception systems to make sure that it doesn't collide with people. So there's a safety case to be made. But again, this is sort of where we're at with control and safety and traditional methods in terms of actual deployable systems. And that vertical line there is this line you have to get across to deploy a system. You can do all the performance you want, but if you don't have the safety case, it is not deployable in practice. So what we need to do is find this Pareto optimal sweet spot. How can we get the performance that we're seeing from these learning-based systems while having the guarantees that we get from control-based methods? And that's what this workshop is about, in my mind, in a nutshell, is we need to really bridge this divide. And so this conference, too, has been early to this idea of learning for dynamics and control, but I think we need to think about it the other way around as well, dynamics and control for learning, right? We need to think about a dual bridge because it goes both ways. It's a two-way street. We need to have a constant dialogue between learning and control, if you'd like, back and forth. Because control, in a nutshell, sits in the middle. AI is on one side, again, pushing data, pushing performance without any guarantees, or if it has guarantees, they're stochastic, it's going to be corner cases, to robotics, which needs formal guarantees to be deployable around people. So we can bring in two, I think, really fundamental things from the control side. Explainability in learning. So by having control methods guide learning, we get an understanding of what the learning will do. We also can get formal guarantee about learning-based systems. And conversely, on the back end, when we take a learning system in, we can get guarantees on the actual robot, even when running learning-based methods. For example, if you safety filter, an RL controller, you can still make a formal guarantee of safety even if your RL doesn't have that guarantee, right? So this is what it all comes down to. So let me start and kind of walk through the day. So control. So first, starting with control, I think people forget sometimes that we've done a lot with control. Like there existed a world before AI and learning in the last 3 years, including things like making robots walk and making them walk quite dynamically and quite nicely. So this is now 10-year-old video, and it's still not bad, right? And this is all based on hybrid systems theory, control Lyapunov functions. I mean, it's good old-fashioned control. It was describable. It was optimal. This was actually the most efficient humanoid robot walking that existed at the time, and it's still pretty far up there. The caveat is that it's fragile. So this got to work on the treadmill. We could get it to walk for a couple minutes. It looked beautiful, but we couldn't take it off the treadmill. We couldn't take it outside. It was a singular behavior in terms of what we could get because our models and the models we use for control are actually inherently sort of limiting, right? Like rigid body dynamics are great, but the world is much more complicated than that. Contacts kill. Contacts are hard to reason about from a control perspective. So what is this workshop about? Well, the thing I've realized, I guess, in the last sort of year and a half is we need to come to terms with the fact that RL is going to be what is put on robots in deployment, especially for locomotion. Why? Because it's robust. So it's a compiler. So you don't use RL to generate the nominal motions. You do it to robustify the motions you already have. Right now, that's being done with human data. But you can do the same thing with control-based methods. So Zach is going to talk next. He's going to talk about CLF-RL, which is exactly this idea. So this is running we got using CLF-based methods, but as the reward for reinforcement learning. And the crazy thing about this video and why I show it is, unlike the Duras video, this was the first time we took the robot outside. It was a Saturday. They said they were going to try it. They had never tried this running outside. They took it outside. We tried it a couple times. It worked right off the bat. And all of a sudden, we're running around campus. That's the kind of robustness you can get by merging control with learning. You can also get safety. The video on the top is showing how you can integrate control barrier functions into reinforcement learning for safety. We can also go the other way around and think about how learning can inform control. I would say this is what this conference has really been about. This is the more traditional view, and it's an important view nonetheless, in the sense that you can take, for example, an existing controller like an MPC controller, and you can use learning to learn residuals, to make it robust to unknown things in the environment, to bring perception in the loop. So for example, on the bottom right here, this is the stochastic CBF stuff that Ryan Costner is going to talk about a bit, where he brings learning into the mix by learning residuals and making guarantees about sort of the unknown parts of the system in the control barrier function. So you can bring it the other way as well to complement that duality. Finally, and this is really important, perception and the role that perception plays. I think a lot of times in control, we don't think enough about perception. I know that sounds strange, but a lot of times we just sort of do all our math and say, okay, we put it on hardware and we do a Kalman filter. But Kalman filters are they don't play the same role they used to. Now a lot of that's being done in reinforcement learning. So the role of perception in the control loops need to be rethought a little with these modern tools. We also can bring in much more complex perception. So on the top, that top video on the left is completely autonomous locomotion using onboard perception, localization, bringing it through an MPC layer, and then bringing that through a CLFRL layer on the bottom for locomotion. So how do we layer these things together? And when you start to understand that layering and how you can bring onboard perception, and you can start to think about things like semantic safety, for example, which is really important. When is there a person in the environment? How can you label and tag that person, and how can you fold that notion of a person into the safety case? So this is also work on the top right is work where, again, it's sensing humans in the environment and reacting. Same on the bottom, where humans are sensed, tagged, and then there's extra avoidance behavior that's put around the humans to make sure there aren't impacts with the human. Because in the end, again, remember, the goal is safe deployment of robots, and the fundamental thing about safe deployment of robots is you cannot hurt people. It's the first law of robotics, right? A robot can never harm a person. So we need to have semantic understanding of the environment to know when there's people, and then act differently when we have that understanding. So that's how these pieces fit together. So I know this looks like a big diagram, but I think this diagram's really important to understand where control and learning are sitting relative to each other. And the way I describe it is this is a sandwich. Every layer of learning needs control. Every layer of control needs learning. And you have to pass these things through each other. Control, learning, control, learning, control, learning. And this has to happen up and down the autonomy stack. I didn't talk about it much, but the same is true as you get up to decision making, to interfacing with LLMs. That needs to pass down through control layers as well, which needs to pass to learning layers, things like reinforcement learning, which needs to pass back through control layers, things like CBF safety filters, finally to hardware. So we need to understand this architecture, which is sort of represented here in this broad level, to understand how to really make things robust to deployment. And again, this is what today's about. There's three pieces. There's the three pieces I talked about. There's how do we take control to learning? That's the first bit. That will start this morning. Then how do we do the second bit, which is learning to control? That's sort of, let's say, the more traditional method, but still really important. And then finally, bringing these higher level ideas in from perception, and how does that fold into this picture? And that's the last talk of the afternoon, or the morning. And so the final bit I'll mention is, again, why does it matter? And I think as a control community and as a learning communities, both, there's really important ramifications to what this means. So I just want to close with this final slide, in that I mentioned control to learning and learning to control. And the point is, when we can really fuse these together, we can enable really rapid instantiation of ideas that are both formally justifiable, but also work in practice. And that's sort of the holy grail of what we're looking for. And so on the right here are 3 videos that came from my lab. And I think the important thing is these videos were all done in the last 2 weeks. And when you start to understand this architecture, this system level architecture for control and learning, rapid development is possible with formal guarantees underpinning it. So just to give an example, this is on the top video there. It's completely autonomous behavior. This is a handoff paper. It's on the archive now, meaning all you do is put in a prompt, and the robot completely autonomously looks at the environment, senses, manipulates with the environment, moves around the environment with a whole body controller. So it's completely autonomous from end to end. The middle one, which is really cool, is a recent paper we just sent to Coral. Again, this is doing dynamic interactions with the environment, playing sports basically. We're thinking about how we can do things like play tennis and play soccer, or football, I should call it. That's the proper term. And then finally on the bottom is actually MPC RL on a new robot. And the point is all of these methods share one common theme, which is using the architecture on the left. And so if we as a control community can understand how to formalize this architecture, and then if we can, in the learning context, convince the learning community, if you'd like, of the merits and the importance of having rigor underlying the systems and not just relying on data, I think that is the pathway to true deployment on robotic systems in the field, which is what we ultimately want. So that's the setup for today. I'm going to pass it to Zach next. I think while we swap, if there's any questions, I can take one quick, but I'm trying to get us back on time. So thank you.
Alrighty. All right. Hi, everyone. I'm Zach. I'm going to be talking about our work on how we put these control methodologies into our reinforcement learning pipelines and get them really deployable on humanoid robots and really dive into the methods behind a lot of those videos you just saw. So, oh, there we go. So, where does control fit in with RL? Well, we just discussed this. I mean, Dr. Ames just gave us kind of the overview here. And we're going to be looking specifically at this kind of control for learning paradigm. And we're really going to be using it in the sense that control is guiding the bulk motion and really it's doing a lot of the heavy lifting. The learning is providing us with additional robustness and really the ability to deploy it easily on real humanoid systems in the real world. So that's kind of the main idea here, but there's actually lots of practical other benefits. And you'll see this throughout the rest of the presentation, but we can do things like avoid tons of reward terms. I mean, there's what, like 15, 20 here. We can reduce this down so that our tuning problem is much, much easier. We can actually improve performance when we embed these control theoretic ideas. We can enable autonomy, and you saw a little bit of that before. And you can even provide certificates of tracking and stability from these methods. So I think it provides a lot of benefits, both practical and philosophical, I'll say. We can start then by diving into CLF-RL, which is control-Lyapunov function-guided reinforcement learning. But before we get into the details there, I just need to draw a picture of where this sits in the RL space. So I'm going to contrast this to what I'm calling classical RL, which is where you have kind of your heuristic reward design. You have all those terms you saw on the last table. You can just kind of make them up, and the idea is that in aggregate, after 15 or 20 of these, they describe the motion you want. And then reference tracking RL is another paradigm where you generate a reference, and then you just use the RL to effectively track said reference. And this is, by and large, right now, done with human data and animation. So CLF-RL, though, is going to go here, and it's going to allow us to answer some questions like, can we do it with model-based references? Can we get performance gains? And then can we actually analyze the structure? If we use a control-Lyapunov function to create our reward, can we analyze this, and does it affect our performance and robustness? So we got to dive into what a control-Lyapunov function, or a CLF, is. So you have to consider a nonlinear system of the form here, x dot equals f of x plus g of xu. And then you can have a Lyapunov function v, which is positive, definite, and continuous. And in our case, we're going to be considering quadratic Lyapunov functions that look something like this, and you just get this really nice bowl. But to make it a control Lyapunov function, you also need to satisfy this condition here, which is saying that there exists a control input, u, such that you can effectively move down your Lyapunov function at a rate specified by lambda. And this is actually like an exponential CLF here. So this is the core idea behind what a CLF is. Then the CLFRL framework as a whole looks like this. We generate our reference, which we'll be using mostly model-based methods to do, and then we formulate tracking rewards using our control Lyapunov function. So these are telling you, hey, minimize the CLF, but also satisfy this decreasing condition that gives us our exponential stability. And then we can train this in RL. We do massively parallelized simulation training here using like Isaac Lab or MJ Lab, and then we can deploy it zero shot onto the hardware. So to just show you how this looks when it works, this is a video from last summer, the robot walking around campus. So this is using the CLFRL controller. And to emphasize here also, there's no online trajectory optimization. There's not even a CLF actually in deployment. It's just a neural network that we're inferencing, but it's trained to respect and use the control ideas that we embedded into it. And it's robust, it works outside, it can turn, it can walk forward, you can control it, and we'll take a look at more of this walking in a little bit. But we can dive in more to the actual like details, like really what goes into making this system happen. Now really what we have is we have a reference generator, we have our CLF-based reward, and then we can just do pretty vanilla asymmetric actor critic is what we end up using, and we train it with PPO. So the reference generators, in our first paper, we used two different methods, and I'll talk later on about how you can extend to other reference generators. But we started off by using the hybrid linear inverted pendulum, or HLIP, reduced order model. And this is very simple, it's a linear model, so you can actually compute the reference you're trying to track in the training loop, because it's very simple to compute. And we compute steady state references then that we track, or the other one we looked at was taking inspiration from the hybrid zero dynamics method, or HZD, and this manifests itself as doing full order trajectory optimization. And you might imagine that these each come with their pros and cons, right? The HLIP method is easier to compute, but also now you're telling your robot to move like a reduced order model. And you actually end up seeing that in the output. That it looks a lot like a reduced order model if that's what you tell it to do. If you leverage the full order dynamics, you'll get that benefit as well. So to actually do this HZD trajectory optimization, this is actually like a non-trivial trajectory optimization pipeline because humanoid robots are hybrid by nature. So this is like a little diagram here showing what's happening for a running gait where you have both a flight phase like on the left and a single support phase. Then what we can do is we can solve this actually with like Casati for autodiff, IPOpt for the solver, Pinocchio for the rigid body dynamics, and we can actually solve for the full order humanoid rigid body dynamics, and it only takes us on the order of minutes to seconds to solve. It's actually quite quick, all things considered. You can add state constraints, and we can generate entire libraries of motions. And you don't actually need like human data or anything like this. You can just use the trajectory optimization methods. And then, of course, since it's periodic walking, we can just generate a single stride, and we can use effectively the structure of the problem. We know that the next stride is a mirror of this, and it can actually improve the efficiency of the trajectory optimization. So we have our reference generator. So our reference generator has given us desired outputs, YD, which we generally parameterize with a Bezier coefficient alpha. And then we can formulate our CLF-V in error coordinates. So the error coordinates here are the eta. And we formulate that as a quadratic CLF. And we then have our tracking rewards. So the CLF tracking reward is saying, hey, make V as small as possible. And then our decay reward is penalizing you for not decaying at the rate specified by lambda. And then otherwise you get no reward. So it's saying, make the small and also decay exponentially to the trajectory. We end up with just a handful of reward terms. We have the tracking and decay. We have a no slip reward. And then we have just a few regularization rewards, which all have very small weights just to allow that to transfer onto the hardware a little easier. And actually, since this original paper, we've been able to remove the holonomic rewards and remove those last two and make it even less and even easier to tune. We can then compare the actual results here And on the left, you're seeing our HCD CLF. And on the right, you're seeing the heuristic baseline. This was effectively the RL controller that we had cooked up in the lab before we did the HCD CLF. What's cool about this is that both of these controllers were trained with identical domain randomization, the same number of iterations on the same computer and being deployed on the same robot. So the only thing that changes about them is our reward design, and we go from just our hand-tuned one that we had used before to our control-guided reward design. And we actually get significant robustness. You can see the other one can't even complete the course. It drifts so far off we didn't have enough space and we were running into the table. And we found that our HCD CLF-based policy was just much more robust to this structural disturbance. If you can't see, there's a backpack on the back and it's loaded with a weight. That it was, was in the domain randomization, but not like part of the nominal model. So we can take this robot outside, and like I said, it can hold a weight pretty well. So we actually were able to attach, in this case, an entire other robot to its back and have it walk around campus quite robustly and navigate through doors and on sidewalks of different types, on slopes and things like this. We always get asked then, like, okay, you're putting a CLF into the reward, like, do you get any kind of guarantee? Is there any kind of analysis you can do here? And we can view the problem, the RL problem, as a discrete time optimal control problem. So we take our CLF reward from before, we formulate it now as an optimization cost, and this is like a slightly simplified version just for the sake of the analysis, but it has the core terms, minimize the V, satisfy the decay rate. Then we have a discounted infinite horizon cost, which is the exact formulation you use in RL. We have to make an assumption that there exists a CLF for the system, and this is structural about the system, but there's many ways to look at this. If it's fully actuated or depending on its other properties, you can derive the CLF. And then you need the value function to be finite and continuous. And then when you satisfy both of these assumptions, you can actually end up with a guarantee of exponential stability. So we show that the value function for the discrete time optimal control problem is a Lyapunov function for our system, and this gives us exponential stability. We can numerically verify all of this. So this is a simplified toy problem. This is like a double integrator going to a point, but it's actually optimized using the CLF RL costs. And we can show the exact same thing. We show similar results too in continuous time. So this really gives credence to the fact that there is like underlying structure then that we're able to analyze and exploit when we embed these control methods into the RL problem. So we did walking, and then we wanted to see if we could make the robot go a little faster. So we were trying to push the speed. And this is running on the robot in our lab here on the treadmill, and it gets a full flight phase and a full stance phase, and it runs just under 3 meters per second in this case. This is using no human data, no animation. It's the trajectory optimization and the CLF-RL pipeline deployed onto the robot. But here we also really had to leverage the hybrid systems nature of the problem, because there is a hybrid system. As you can see here, you're bouncing between the single support and the flight phases. You have to optimize for those impacts. We did this, and this is great. Then the question is, can we get additional benefits by actually putting in human data, but without losing the nice structure and analysis that we have gained from the CLF-RL pipeline? And the answer is yes, we can. It's actually not too difficult. So we can take, say, kinematically retargeted human data. So maybe you've got a mocap system, you retarget it onto your robot, but it's like noisy, or you're like foot sliding around and things like this, but that's okay. We can identify a subsegment that's like most periodic that we kind of want to mimic. We can pull out contact information, like if your foot is in or out of contact. So say we can extract the hybrid sequence for this running gait. And then we can optimize, and we can optimize with the same optimization routine that I talked about earlier. And now we are able to like clean the data and make it much nicer, and we can actually extend this into a whole reference library. Then we get to use the CLFRL pipeline again. We have our reference library. We put that into our CLF reward. We can do another asymmetric actor critic, push it through PPO, and we get to deploy it onto the hardware. And in this case, it was actually controllable enough where we can put a high-level controller on it and use it as in autonomy. But first, just to show you the result here, you might notice that this running looks a little different than the running I showed you 2 slides ago. And it is, right? Because this actually is coming from a human prior, but maintaining dynamic feasibility through the entire pipeline. And we were able to run faster. In this case, we could go up to 3.3 meters per second. And this robot's not quite full human size, so it's pretty fast for it. And we are able to go for longer. We were able to run hundreds of meters around campus. Also, I'll just kind of let this other video play out here too of it just running around campus. You saw a little bit of it before. But we then are able to optimize this human data. We can generate entire libraries of references. And by using these, by using this trajectory optimization, we got all this running from 0.3 seconds of human data. That's all we needed. It wasn't much. So you can also view this as a way to give us additional, I'll say, data through the control ideas. We get to clean the data, we get improved tracking, and we can preserve style. So this control-guided learning improves performance. The CLF is the blue one. That's our reward. And then the orange is the mimic style reward, which is what other people in the robotics community have been doing. And we're able to improve on tracking error across the board, and then also using our dynamically optimized human data is better than using other forms of trajectory optimization or just kinematic data as well. Like I said, this enables autonomy. So we actually are able to get fully autonomous running. There is no one driving this. It is able to sense the environment with a LiDAR. So it senses both the blue thing on the left and then the group of things and the person on the right. It uses an MPC with a CBF constraint, and it's able to just pass that to our running policy. And so we can now fully autonomously run in the real world and avoid collisions. Then we can use CLFRL for more than just walking and running. We can do it also for things like discrete footsteps. So this was recent work here where effectively you have your reference generator are the first 2 blocks. You do things like footstep planning to choose which block to step on and what the timing of stepping on that block is. You can then track that with a reduced order model. You can use an HLIP or LIP type reduced order model. You put that reference into your CLF, and then you can train, in this case, a privileged teacher and distill it into a student that can actually be deployed. We find that the CLFRL here achieves similar performance with less rollouts, making it more efficient, and overall, against the model-free baseline here, achieving a smoother and more efficient walking locomotion motion. This deploys onto hardware too, with the perception in the loop. So you can see the depth camera is observing the surroundings, and it's actually able to just fully walk across these planks quite nicely and steadily. It's also been done in other ways here using different reference generators, which give us, you'll see it's a bit of a different style of locomotion here, but it's able to also achieve, once again, this discrete footsteps quite fast and over quite complex and varied terrain here. Then we use this also for autonomous stair climbing and navigation. You'll see on the top left, that's what the robot saw. That's the LiDAR. And then this particular CLFRL method used a reduced order model that is terrain dependent. So in the simulation, we have terrain ground truth. You can plan with your reduced order model perfectly, and that can guide your training. And then we can have this thing walk all around campus. It's able to sense its environment, localize itself, and go straight up the stairs all by itself. Once again, this is fully autonomous. I'll let this play out here, going to the up the second set of stairs. We talked a lot about how we can get performance from our control-guided learning. Then you can also, on the flip side, do it for safety using things like control barrier functions. So we can talk now about CBF-RL, which is control barrier function guided RL. First, we just have to make sure we're on the same page about what a control barrier function is. So you consider a system model, x dot equals f of x plus g of xu, the same nonlinear system. Then you can write safety as set forward invariance. So consider a set C. The idea is if you stay within your set, you are safe. You can define the set C by a function h, shown there. And then if your h dot satisfies this condition, if it's greater than or equal to negative alpha h, you get that your system is safe, your set is forward invariant. This is a little just a diagram here of showing exactly what that looks like as you approach your safe set. And then we can do CBF-RL, where we train an RL policy, and in the training, the output of the RL is filtered with a CBF. Now, you have to compute the CBF in real time. You have to compute it in the training loop in this case. So you can use, luckily, the closed form solution for a CBF-QP because that exists. And in the paper, they proved that you can do that. You can use the closed form solution from the continuous time version of the CBF, even though your RL is working in discrete time. And then you also end up penalizing it for using the safety filter. So it learns both what the safety filter looks like, and it also learns to not violate it. And in this case here, we're looking at, this is CBF-RL so that the foot doesn't slam into the next stair. And then you can have this thing go up a set of stairs without having its foot slam into the next step. So with that, I just wanted to thank everyone who worked on all these projects. And I think I'm about out of time, so thank you.
Great. Thanks, Zach. It was a great overview on the learning side. I think we'll flip it up here and maybe take questions at the end so we just stay on time. Good? All right.
Just need to unlock the laptop. Okay. Hi, everyone. Thank you so much for having me here. I'm Mahati Anand from the Learning Systems and Robotics Lab at TU Munich. And I would like to continue Zach's talk on using control theory for guiding learning-based algorithms. And what we will do over here is look through other core methods, quite similar to also what Zach has already presented, but this time also looking at different robotic platforms. So just again, a quick recap. We already have now a very good intuition of why we need theory-guided learning. So from control theory, we basically end up with really nice, simple controllers with guarantee. And this happens because there's a lot of structure in the system itself that we generally use, coming from the model, from the well-defined constraints and system properties like stability and so on. But in the real world, we want to perform complex, sophisticated tasks. And machine learning really makes this happen. But unfortunately, though it uses large amounts of data, there is no structure that is involved. And the idea behind theory-guided learning is to basically somehow encourage the structure during the learning process itself to encourage sample efficiency as well as performance of the algorithms. And similarly to what was already presented, we also want to ensure that some constraints are satisfied, so primarily safety constraints, input actuator limits, and so on. And then finally, what we can also do is impose structure directly into the learning-based algorithm via, for example, control-Lyapunov functions or Lipschitz neural networks in order to get really good closed-loop behavior. And the result of this is basically a learning algorithm, a learning-based controller that essentially gives high sample efficiency, improved performance, as well as safe and reliable behavior. So we will go over these 3 points one by one, starting with encouraging structure to improve performance. And before I do that, I would like to quickly talk about safety filtering. So we already got an introduction of this by using control barrier functions. And this basically tries to, it works with any arbitrary unverified controller, including learning-based, and uses a quadratic program formulation to modify this controller so that there's a backup for safety. Right? But in general, this is usually myopic and also requires the computation of control barrier functions. So what do I mean by myopic? It's just that at each time instant, there's a safety filtering that's happening without considering the future time instance or without any prediction of what could happen in the future. And this could cause essentially chattering in the safety boundaries and also perhaps sometimes feasibility issues. So one way to alleviate this is to use predictive safety filtering instead. So here, safety filtering is described as a model predictive control problem. So you have an unverified controller that you can predict trajectories with up to some horizon. And then you can essentially check whether this trajectory is safe and whether it's safe, and then provide, again, a least restrictive control action in order to bring it to safety. And essentially, at the end of the prediction horizon, so you want your set of the predicted state to end up in the safe terminal set that guarantees recursive feasibility. But this is usually done with the help of the system model, so you really need the system model for this, but this is not always available and fully known. So there's a robust way to formulate this safety filtering problem. And here, what you do is consider that you have some kind of a known nominal model and an unknown model that lives within some uncertainty set W. Then you can basically robustify this predictive safety filtering problem. So over here, the objective function is simply to provide the least restrictive control action. And K refers to the predicting the time instant, and I refers to the prediction around this horizon, the predictive time instant. And what you have is basically constraints in the form of system evolution with the nominal dynamics, and then you essentially also need robustness to uncertainty, and this can come, for example, with set-based propagation over this uncertainty set. And then you, of course, have safety constraints, which could include your state and your actuation constraints. And finally, the requirement of state to move into the robust terminal set for recursive feasibility. So having introduced this, we can actually talk about how we can utilize safety filters for training RL. And I think this was also really nicely touched upon in the last talk. So the idea is that you have an arbitrary RL controller that you execute in some environment, and this environment can introduce safety constraints. So what you would want to do is basically filter the unsafe actions generated by RL in order to make them safe. And this is basically your safe controller, right? But you can also flip the script and say that this actually is the RL controller is now operating in a safe environment, right, which has the safety filter in it. And now, since it's operating in the safe environment, you can actually train the RL controller directly in the safe environment, right? So the question that we ask is, can training on the safe environment with a safety filter improve sample efficiency and performance? And the answer to this question is yes, indeed. Because if you train directly with a safety filter, right, there are no crashes during training, and you always anyway use a safety filter during execution as an additional feedback. So it eliminates distribution shift when you train directly with a safety filter as well. Right, so what are the considerations that we have for such a training algorithm? So first of all, we want to prevent violations during training, and this can be done by modifying your reward function suitably by introducing a penalty on safety corrections. So I think this was also pointed out in the last talk. where basically this encourages RL to generate training actions automatically. So the the penalty on safety corrections is basically triggered every time the safety filter is being used, and as a result, the RL controller will learn to take safe actions to begin with. And the second thing is improving sample efficiency. And this can be done by rolling out episodes directly from the set of safe states and using only feasible trajectories into your training algorithm. So having said that, let's see how this performs empirically. So you see over here with this first plot that as soon as you start using your safety filter actions during training, the convergence is much faster and the expected reward is also higher. And when you add this with safety reset as well as penalizing corrections, then it's also much more improved. So here you see the application of this safety filtering in training in a multi-agent setting. So here the requirement is that these 3 mobile robots, they make a formation within the centroid, right? So it has to make this triangle formulation around the target centroid. And you see that they perform, with the safety filter included, they perform really well. And something to highlight is that this is something that's a very difficult problem to solve with standard model-based controllers and even MPC. But by using reinforcement learning and, of course, with safety filtering, we get a much improved performance that is also safe. Right? Moving on to the next part, we will look at how we can impose safety constraints within the learned policies directly. Right? And so far, we've only spoken about RL, but we can also apply these safety filtering techniques beyond RL, particularly to generative learning policies. And why we would need generative learning policies? Of course, they have a good ability to learn from multimodal data distributions. They can perform imitation learning directly from human demonstrations. And these days, you can also have textual prompts just guiding robot actions and also have some semantic understanding. Right? So we will start with diffusion policies as our first generative model. And here, in a diffusion policy, you have data coming, again, from different sources, from multimodal distributions, so coming from states, images, anything. And then you have basically all of this put forward in a forward diffusion process and turned into noise, right? Then you have a denoising process that basically predicts the noise and tries to imitate your original data distribution by learning a conditional trajectory like so, via, for example, neural networks. So what you get at the end are robot actions that live within the that approximate your original data distribution. Okay, so far we haven't really spoken about constraints. And the thing is, diffusion policies, they cannot incorporate any constraints. So if you introduce novel constraints in your environment, then you no longer have satisfaction of your constraints. So one way to solve this problem would be to use this diffusion policies in a receding horizon fashion and use the safety filters that we talked about earlier. So when you solve the diffusion predictive control in a receding horizon fashion, what you would do is essentially learn a conditional trajectory distribution coming from that imitates your data, and then basically apply this diffusion policy in a receding horizon way. So what you do is basically observe the current state, and then sample the trajectory from the conditional distribution that you've learned, and apply the first action until basically the goal is reached. Right? And now we will look at how we can incorporate the constraints that we just talked about. So you have some set of constraints which live in Z. They could include your state input constraints as well. And you have these novel constraints that you didn't have during training. And you have a dynamics F, right? This is your system dynamics, but also there's some model error, right? Some unknown or unlearned component. So what you could do to introduce robustness is tighten these constraints Z into this Z bar F, and this accounts for the uncertainty that you have coming from the model error, right? And when you do the denoising, you can project the noisy trajectories into the safe tightened constraint set and sample trajectories directly from this set so that your actions that are generated are guaranteed to be safe. So here we see a vanilla diffusion policy. So the learned data distribution is basically over here as a diagonal, and then we introduce this novel constraint. And of course, since you learn it in a vanilla way, there are no constraints incorporated, there's no way to guarantee safety. So there's one way that you could incorporate constraints, and this is directly within the cost function in your denoising step through a guidance. And here you see that, of course, the constraints are somehow being incorporated, but you do not have any formal guarantees. Now, when you start applying projection, so for example, if you here apply projection only in the final step of your denoising process, you already see a very good improvement in safe constraint satisfaction. And if you do it in each projection step, then it's also getting better. And more importantly, you see that here your learned trajectories directly match the data distribution better than when you do projection only in the final step. And this is a good way to basically incorporate constraints while retaining guarantees, even with generative policies. And this is a simple simulation video showing the same. So in the first case, it's a vanilla without any constraint incorporated, and it quickly fails. Whereas in the second video, where diffusion predictive control is being used, you have constraint satisfaction and obstacle avoidance. Okay, but there is still one limitation of this, this method. It is basically that you're still modifying your actions, right, from the nominal controller that you have and projecting them into this tightened constraint set, which could cause modification of your original path or your original intended path that your diffusion policy generates. And as a result, you could end up in out-of-distribution states and causing failure. So one way to do this is to not modify the controller itself, but instead use a fail-safe stopping motion without any path modification. And this way, the robot will stay on its intended path while still retaining safety guarantees. And here in this approach, I won't go into details over here, but what we do is basically use a reachable reachable occupancy set to detect collisions. So you have a reachable set for the robot and for the obstacles, and you check if they're intersecting in order to get information on the collision. And compared to a regular safety filter using CBF, which employs controller modification, here you see that the generated trajectories are closer, are staying within the distribution of the data and avoids out-of-distribution failures. And now, moving on, I will also talk about using safety filtering with large language models with this really cool example of a drone choreography problem. So here, we want to use LLMs to prompt the drones with some song and ask them to dance for it. And then basically, the LLMs will generate a set of primitive motions. But this, of course, is not going to give you any safety guarantees or does not consider the dynamic feasibility of these trajectories that they generate, because there's no actual actuator limit satisfaction. And in this case, you can employ predictive safety filter idea to generate feasible constrained trajectories. So what you have over here is basically a language-based choreographer that turns your music, the information from the music and your textual prompt into a set of motion primitives that are generated by the motion generator. So for example, you could have motion primitives like the drones dancing in a spiral form or rotating or in a wave or so on, right? So these motion primitives generate trajectories, and these raw trajectories are fed into an optimization-based safety filter, the one that we've been talking about all this long, using a predictive safety filter. So here, you can use identified system dynamics, but of course, if you want, you can also robustify it, and basically have constraints that ensure that you can match the reference trajectory up to your desired order of continuity, and then you can also have constraints on the state, actuator input, as well as continuity and smoothness constraints. So once you do this, this is what you have. So you basically get a text. I will maybe keep quiet until the music plays. So what you saw in that video was there was a textual prompt given to the language-based choreographer, please dance to the song royalty, and then the drones generated the performance based on motion primitives that you had, like wave, rising, spiral, and so on. And these were basically filtered to ensure collision avoidance between different drones, and to also ensure that the trajectories generated were smooth and feasible. Right, so finally, I would like to get to the part of imposing structure directly to improve system behavior. So far, we employed safety filters during training and during execution in order to make sure that your constraints were satisfied. But your constraints, for example, if you want some system properties, can be directly incorporated into your learning architecture so that you have guaranteed closed-loop behavior. So imagine that you want to design a black box, and this could be your dynamics, this could be your controller, and so on. And given an input, you, at the end, want some desired system output. And this could be, for example, as a reference model that you want to implement. Right? So within this black box system, you can directly incorporate structural constraints. So if you have a neural network and you want, for example, robustness guarantees, then you can ensure that these neural networks are leap sheets. Or you could also, if you're learning a dynamical system, then you could also learn a neural network dynamical system that is by construction stable or safe by using Lyapunov and barrier functions. And similarly, you can also incorporate physics in order to get some physical reasoning. And the result of this is basically a black box model that has closed loop guarantees and gives you a desired system output. So in the interest of time, I won't discuss this quite a bit, but you see an example over here where we have a stabilization task where because of model reality gaps, the stabilization was not very well performed with a baseline. But when you learn a leap sheets neural network that gives you some sort of stability guarantees, you see that it performs much better. Even in the presence of disturbances like wind disturbances or tapping. And going beyond, there's also a tracking task with circular trajectory, where a circular trajectory needs to be tracked, and you see that with a leap sheets neural network. So here, by construction, you can bound the leap sheets constant of the neural network, and which gives you finite stability guarantees. And this is another experiment where we actually use neural networks to learn robot motion plans. So the motion plan itself is described via a dynamical system, and this is basically learned in conjunction with Lyapunov and barrier functions to get some kind of stability and safety guarantees. And what you see over here, I will forward it a little bit, is that even in the presence of perturbations, so you have, so here's where you will see that the robot is being perturbed slightly, and despite of that, there is still convergence, and the task is being performed as required. And so here, basically, the dynamical system directly maps the motion of the robot by giving appropriate velocity commands to the position commands. And that's basically my time. Thank you very much. I would like to leave with a quick summary on theory-guided learning. So what we saw in this talk was to encourage three things: encouraging structure directly into your learning to improve sample efficiency, imposing constraints after learning in order to get safety during execution, and then finally imposing structure for guaranteed robustness even with using black box models. So thank you very much. And so we have the next speaker if we do not have any time for questions. Yeah.
Sounds great. Let's see if that's going to go up there. There we go. Hi, everybody. So we're starting into the second part of this tutorial here. That first part was control for learning, guiding how we do our machine learning, and this is flipping it. Now we're doing learning for control, so going in the other direction. Just a quick self-introduction here, if my slides will click. That's me. My name's Ryan Cosner. I'm a new assistant professor at Tufts in mechanical engineering. I work on these ideas of control, learning, and robotics. I lead the safe and performant autonomous robotics and control group there. So we're really thinking about the same kind of topics that we've been discussing so far. And this is a group of people who've been fantastic to work with, and all of them are appearing on the works I'm going to be discussing today. So huge thanks to all of these folks and their contributions. This was the same slide that Zach had, just a quick refresher. I'm going to skip over most of this, but we're going to talk about safety in the context of control barrier functions. We have this system model, in this case, this control affine system model. We describe safety as the forward invariance of some set, so this green region that we call safe. We're going to then use a function h and say that as long as that function h is positive, we're in the safe region, or non-negative. So we now have this value associated with safety. And we have a associated theorem down on the bottom left here that says if we can constrain the time derivative of this safety value by negative of its current value, we achieve safety. Intuitively, this is just lower bounding by an exponential decay. So as we approach the boundary, our value decays, but we're forced up in our time derivative, so we can never actually cross zero. Okay. That's the flash talk on barriers. So we have this nice theorem that says we get safety in this theoretical context, but how do we transition that to the real world? How do we retain these guarantees under real world uncertainty, bridging this like theory to real gap, theory to sim to real gap kind of things? So kind of the traditional way of doing this is kind of from the robust controls perspective. So if we have our system dynamics that we had before, x dot f of x, g of x, u. Now we're adding a disturbance term. Here it's matched, but you can do different forms of uncertainty, of course. And we are then going to bound the worst case possible version of that disturbance by this upper bound delta here. And if we do that, there's this nice result that says now you have an alternative safe set. So instead of keeping the original set safe, you now have this expanded version where instead of being above zero, your safety value stays above negative gamma delta eta. So there's a bunch of other terms that now pop in here, but we visually are just expanding our set. So as this worst case bound grows, the set that you can render forward invariant is also growing, assuming that you can satisfy these conditions. What you can do then to try to recover some of this safety is tighten your constraint. So there's this 1 over eta term here where if you just push eta towards zero, this is going to make this constraint tighter and tighter, and you can recover more of your original safe set. So the method here is essentially you're bounding, and then you're trying to cancel all of your uncertainties, and you're canceling the worst case version of your uncertainties. What's nice about this is you do get this robustness via worst case over approximation, so you get this nice safety guarantee. The problem is that it's really conservative. You're essentially assuming the worst thing is going to happen all the time forever, so you're going to stay arm's length from everything, which isn't really how we want to deploy our robots. We want to be able to incorporate some of the uncertainty and work with it during our deployment. And so that that brought me to change frameworks. So this is this robust control worst case bounds over approximations framework. And I wanted to handle uncertainty that potentially isn't bounded. And I want to be able to work with the risk associated with it when we can't directly cancel these uncertainties. So we might have to deal with things that are unbounded and might be random. If we have a Gaussian uncertainty associated with something, this has unbounded support, we could potentially sample something really massive that we can't capture in this worst case bound. And we can't directly model this. Like, it's a random thing. We don't have a way to directly predict the exact value. So I wanted to switch from a deterministic worst case version of safety to a stochastic notion. And to do that, there's a lot of things you have to change in the paradigm. So the continuous time CBF framework looks like this with our additional disturbance term. Our goal in this case is forward invariance, and we're achieving that via this time derivative lower bounding constraint. And to switch to the stochastic framework, we switched to a discrete time version of our dynamics. We spent a lot of time thinking about stochastic differential equations, and we realized for robotics we thought this worked better because we don't have the infinite bandwidth assumption that kind of comes with control for stochastic differential equations. So we felt this fit our robotics application better, but when you switch to this, because of this limited bandwidth, you wind up able to always guarantee forward invariance with 100% guarantee. And so we need to switch our understanding of safety to be a little more nuanced. And in this case, we have a bounded risk of failure over a finite horizon instead of this infinite horizon guarantee. And then our constraint also becomes different because now we have to deal with the distribution of the uncertainty. This is one potential notion of a discrete time control barrier function constraint, and this is the one that I'm going to work with, and I'll tell you why. So this particular constraint is really nice. We've got this expected value of our next value of safety. So what is h given the change in the state due to the dynamics and the disturbance, conditioned on the current state. And we're going to lower bound that by a similar decay condition. What's cool about this is it directly relates to super martingales. So on the left-hand side here, we've got rollouts of our safety value, and our safety constraint is staying above 0. And then what we do is we transform this, and we write now this W, which is a super martingale, and our constraint now becomes stay below this line. The super martingale just being this stochastic process that has this inequality on its expected value. And now that we've made this connection, it gives us access to a bunch of stuff in stochastic process theory that we can start to use to make our guarantees. So we have a martingale concentration inequality we can apply here to now bound the spread of our safety values. In particular, I leveraged Ville's and Friedman's inequality. There's a bunch of different concentration inequalities you could use. And this allows us to get probabilistic safety guarantees for our stochastic control barrier functions, where we're upper bounding the probability of safety failure over a finite horizon k, given that you started at some initial position x0. And we went on and looked at a bunch of different concentration inequalities as well. This is work with Paul Mesters and Blake Warner and Aaron Ames. You can see on the bottom where we, under different circumstances, looked at what might be a better alternative constraint that you might want to use, or concentration inequality you might want to use. But what ends up coming out of all of this is you have different things governing the probability bound that you get at the end. This is a function of your initial condition x0, the horizon length that you're operating over k, the distribution information, so like the average value, the covariance, it could be the full density function, the decay rate, so this is what you get to modify as your engineer, so how fast your safety value is allowed to decay in your constraint, and then the number of samples you're going to use if you're doing a scenario approach or something like that. And what's nice is it really gives us a different perspective on safety from the worst case bounds. So here is our level set expansion on the x-axis, and then on the left-hand side is the unsafe probability upper bound. And as you might expect, as time goes on, our worst case is just 0 to 1. After we could have received a bunch of worst case disturbances, we get a really vacuous bound. And over time, we diffuse our probability mass, so we wind up with something similar, but especially near the beginning, we are able, especially near the beginning, we get very useful probability bounds, while our worst case bound said, oh, the worst thing happened and I can't guarantee anything. So this adds an additional nuance where we can see the risk that's changing through time of safety for these different level sets. And just as an example use case, we've got our quadruped here, and it is assuming that has unicycle dynamics, so it can rotate and move forward with velocity inputs. And it doesn't know that it's on this pallet or that there's these slippery, like ice things, these white plastic pieces. And so when it walks over them, it can slide to the left. If it doesn't account for that, it doesn't account for this disturbance to its dynamics, it falls off the pallets, it moves off to the side. But what we did instead was we sampled a bunch of these, we rolled out the dynamics, got samples of the disturbances, and then are now adding robustness to this based on the stochastic control barrier function constraint. And as we do this rollout, we're now robust to the effects of this disturbance. We also did something similar on our quad rotor drone here. So there are two perspectives, third-person view on the left-hand side, and on the right-hand side, this is actually the visual information that the robot is using to play dodgeball. And that's me throwing the dodgeball. Our safety criteria is avoid getting hit, and then also avoid hitting the ground. And we're going to use onboard vision for this obstacle sensing. We're using Facebook's segment anything model to detect the ball and track it through space, using an onboard depth camera to get the estimate of its relative position, and then estimating its trajectory using ballistic trajectory plus a Kalman filter. And we're assuming that that Kalman filter uncertainty distribution is the correct uncertainty distribution. And we're enforcing this stochastic control barrier function constraint on the belief dynamics. And we get some nice behavior here, moving out of the way to avoid getting hit. I love playing this video because I get to play it at 20% speed. Most often robotics videos get played sped up, but I had to slow it down to show you the cool behavior. And so we're enforcing this stochastic control barrier function constraint on the belief dynamics with the Kalman filter based uncertainty and getting our nice dodgeball. But sometimes this distribution information isn't necessarily going to be nice like this. We might not have a static disturbance like we had with the quadruped. We might not have a nice way of modeling the uncertainty like with our Kalman filter. And it can get a lot more complicated. And so how are we going to estimate these distributional parameters or the information that we need in order to enforce this stochastic control barrier function constraint more generally? And what we turned to was generative models. We have tools from machine learning to capture this uncertainty. And the setup for this was having our robot in the real world. So we have our quad rotor drone here now with its added disturbance term. We're feeding the state of that into our CBF safety filter with a generative model attached to it. So the generative model is predicting the uncertainty distribution given the current state. We're putting that into our safety filter and forcing the stochastic CBF constraint, which feeds our input back to our system. And in particular, we used conditional variational autoencoders as our generative model. You could use other ones. We use this because they're really, really fast. We could put this on hardware, run it at 200 hertz. And it was able to capture what we needed. Our things weren't super multimodal, and so we were able to capture the parts of the uncertainty that we needed to capture. And we trained this on safe trajectory data. So we flew our quad rotor around, collected the data, and then conditioned our distribution on the state of the quad rotor so that changes what the distribution spread looks like. Our scenario here is this quad rotor with this water bottle attached to it. And our safety constraint is don't let the water bottle hit the ground. And it knows the bottle and cable length, so we've predefined safety that way. And it has a nominal drone model. Our drone models are pretty good. So we can pretty accurately predict its dynamics if it didn't have this added mass attached to it. The unknowns here are the value of the added mass, the parameters of the water bottle, and its state and its dynamics. So the drone knows its own state, but it doesn't know the state of the swinging mass below it. Our steps are to collect the flight data, train this generative model, this conditional variational autoencoder, and then deploy it with our stochastic CBF safety filter. To deploy it, I'm going to fly it up to a position, perturb it, cause it to drop, and then the CBF is going to catch it. And we're trying to deploy this stochastic safety theorem to get this bounded risk of failure. We first did it with an MLP, so not learning the distribution, but just trying to match the disturbance directly. And we're able to do that okay if we're just dropping straight down. We're just essentially learning the average mass of the water bottle. But if I perturb the system, it can't predict where the water bottle will be just given the drone state. It's a single sample of the drone state. And so we have these collision failures where the water bottle ends up hitting the ground. But if we switch to our CVAE version, where we're now learning not just the average value of the uncertainty, but the distribution conditioned on the current state of the drone, we get better behavior. We're not colliding with the ground, but we're also not, worst case, having to fly 5 feet above the ground all the time. And so what it's doing here is I'm, again, moving it to a position. I'm going to perturb it a little bit, let it fall. It's predicting the disturbance and the spread of the potential disturbances given the current state of the drone. And what's nice about this is we have this additional tuning parameter. So our decay condition in our control barrier function is now our risk tuning parameter. Can use that to modulate how conservative our system will be. This worked really nicely, so we were excited to try it out in new locations. This was a demo that we did for the lab. There's Aaron over to the side. So this was a public demo we did. There's an audience sitting about where you are sitting watching this happen. And we retrained our model, moved it to this other place. I've now gotten more confident, so we're doing some more extreme maneuvers. But this is onboard generative model in the stochastic safety filter, enforcing these stochastic CBF constraints. And we switched out the water bottle because we had to have the Caltech logo on there. And we had a bigger flight space so we could do some more dynamic maneuvers. It was pretty fun. So that was on the quad rotor, but we also wanted to see how this generalized, applied on other systems. And we looked towards our humanoid as a potential other application. Here we were defining safety with respect to the center of mass, and so we just put a radius around the robot and said we wanted the robot to stay that distance away from everything in its environment. The issue that we ran into was that we couldn't just condition on a single value. The humanoid is not, in fact, a single integrator. It is much more complicated than that. It has contact dynamics. It has inertias associated with it. And so in order to get a good understanding of the distribution that was useful for us, we had to condition on a history of the state. So we built a conditional variational autoencoder trained, or that's conditioning on a history to approximate the disturbance, including these things like inertia, contacts, and things like that. And we put this on hardware. So on the bottom left, you can see what the robot is seeing. So it's got this LiDAR, and then it's segmenting obstacles, and it's generating these different safety constraints with respect to all of these red dots. And then it's avoiding colliding with people, colliding with obstacles in the environment, using this stochastic control barrier function with the generative model inside of it. And so just quick takeaway, so I don't hold you too long before y'all get coffee. What we did here was we accounted for uncertainties with our stochastic CBFs, which gave us nice parameters and a way to understand this Pareto frontier of robustness and performance. So now we have this risk. It's not just, are we safe or not safe? We have a fluid way of understanding the decay of safety as our disturbance is growing. And we were able to capture the uncertainty in this with generative models and put that into our real-time controllers. So that's what I had to talk about today. Thanks for sticking around. Hope you enjoy coffee, and we'll see you back for the next session.
Yeah, in a minute.
Yeah?
Yes, now we can do questions.
We can take some
for a
questions,
minute.
okay.
I think we're back on time. Great
Perfect.
job. So let's thank all the speakers again for pulling us through. Good job. We can take questions for a few minutes now before the coffee break for any of the speakers. The first part of the tutorial. There's 0 questions. You can kick it off.
Thanks. This was very interesting. I guess one question I have is about I would call it quality of the Lyapunov and the barrier functions that you have to guide the learning, right? So what is your experience there? I mean, to begin with, you have to have a valid CBF or CLF. How can you ensure that? I saw that you used reduced order models, but how, is it valid for the higher order system as well? And then how restrictive can it be? Can you also fine tune? Because it may interfere with the behavior and optimality. Just some comments on that.
It's a great question. I mean, so for reduced order model, in fact, in general, we're using kind of the HCD paradigm. So we assume the system is partially feedback linearizable. If it's fully linearizable, that's even better. And then you just synthesize the CLF on the outputs. So you just do that like, you have like your outputs transpose P, your outputs for the linearization, and then you bring that back to the nonlinear. So the point is you can automatically synthesize the CLFs for the nonlinear system, and you know they're valid. And they are nonlinear because they're on the outputs, which might be nonlinear functions. So they're not just like linear CLFs, but you're absolutely right about the other part, which is, so you know they're valid, so the theory works, and they work pretty well in practice, but they're definitely suboptimal in terms of like, in general, you would want to have, the better the CLF, the better the reward, the better the thing in practice, the better the robot in practice. So there's obviously a huge opportunity for doing better CLFs, and then that gives you even better rewards. There's a huge, and if we could pull in that pipeline that Control has been working on this for, 40 years, right? CLF synthesis, that would definitely make things better. Yeah, it's a great question.
Specific you may, in this context of guiding an RL controller that you could do to make them less conservative? Or is it just in general you want to increase the, I guess, safe set in some sense?
Yeah, I think for the barrier function case, the optimality becomes like really important. Right now and that's a more complicated question too, because to do safety filtering like CBFRL, you have to do the CBFs in rollout. So what we do is we have a reduced order model that we use for the rollouts to impose the CBF condition. So it's a simple like single integrator, and then the CBF is like a really simple like distance constraint essentially. So that's all like the most basic vanilla version of a safety filter you can imagine, because you need to GPU parallelize. If you break the ability to GPU parallelize, you may as well not do RL, right? Like, I mean, CPU RL is just going to be like 10x slower. So that means you're working with really simple models and really simple barriers, which means they're very much not optimized to the behavior of the system, which means they can be overly conservative, which means you're going to constrain the training, right? Which means you're gonna potentially, especially for doing things that are very like tight safety-wise. Like it's one thing if you have a robot walking and you don't want to collide in a big open space, but actually we're seeing this right now where we're like training like humanoid robots to go through doors and things. And in that case, all these things matter a lot. Because if going through a tight space where you have like a little bit of distance on each side, then all of a sudden the way you synthesize your barrier matters, right? But I think, Zach, I don't know if you want to add anything, because you're the one that does the training on all this stuff, right?
Yeah. I mean, I guess just to address that, yeah. So I think as you improve your CLF quality, I think your training will get better, and I think there exists better CLFs probably where if you have them, you could even like reduce training time on top of this. And so this is like ongoing stuff we're thinking about, so I don't have a concrete answer, but I think it's a very astute observation.
Yeah, I think it's a great question. I think there's a lot of work to do there.
Because you chose quadratic, I guess.
Yeah. We were doing quadratic. Yeah. Better CLF, better training, better barrier, better training. I think this is the feedback loop we can be studying with this like controlled guided learning. I think as an area has huge promise, and that's kind of what today was about. Like this is sort of a new thing. It's not like that hasn't been studied, but it's definitely out of the mainstream. But I think it's the place where it's like the most open ground that can have huge impact like right away. So, all right, now lots of questions. I saw this one first.
You can turn on the podium mics, the mics on the stands as well.
Thank you. Thanks, that was a very nice hour and a half. So I guess my immediate comments would be across two dimensions. On one dimension, I definitely like the idea of using structure in problems. If there is structure, we shouldn't just rely on data. Use the structure as much as you can and then rely on data. Where I'm a little bit unsure about is on safety, and specifically the following. We've seen different approaches to safety, broadly speaking, and I see they are valuable to get sort of better performance in some sense. What I'm not sure about is how valuable they are in actually truly giving safety statements. Mm-hmm. So for instance, I'm looking at this last presentation. It seems to me that if I don't know anything about the dynamics, there's no guarantee I can give, right? So I'm wondering if you can, any one of you can elaborate a little bit more in terms of, what should we aim for in terms of safety? What do you mean for safety? What guarantees can be achieved and what cannot be achieved?
Great question. I'm going to start and then I'll kick it to Ryan because immediate reactions to this. It's a great question. And I think we need to separate out. Remember I talked about at the beginning this layered sandwich? Like actually one of my students recently said it's like Swiss cheese. You have all these pieces of cheese, and every one has holes. The safety case is putting all those together, then you fill the holes, right? And so in this way, what I'm saying is, we're talking about like control-guided learning using CBFs in that. That is just to make the learning aware of the safety, but that is not the safety case. To be very clear, to your point, you need to have a safety filter online in real time, regardless of how safe you think your learning is. There needs to be that other layer that is certifiable, and that's the certifiable piece. CBFRL is never meant to be certifiable. It's just meant to internalize safety so that it can be consistent with the thing you're doing online, so that can be less like constraining. To your question about guarantees, though, you're right. So now you want to certify, and I actually mean like really certify, like ISO standard certify, functional safety certify, which I could talk about for a long time too if anybody's interested, like real certification, these things. And what you're going to need is a CBF, a mathematical, basically a theorem that says that this gives you the correct behavior because you have to satisfy your functional safety case. And then to your question about models, this is a really good question. How do you certify the fact that the model, you might not have a model, it might be wrong, you're safety filtering on RL. And my general statement is that actually doesn't matter that much in the sense that, and it's built on this premise of, we had papers starting in like 2021, 22 on what we call model-free safety filtering, but what that really meant was your model for your safety filter can be very different than the model that your system has or that your RL is using. All you need to certify is that reference signals that come out of your safety filter and head to the next layer in the architecture can be tracked well enough, and you can actually make formal guarantees about the safety of the system. So what I'm saying with all of that is that it's not so much whether your model's right, it's can you make guarantees and certificates about the way your model interacts with other elements in the architecture and make guarantees based on that, and that's what will give you actually a certifiable safety case in practice. Does that make sense? So I don't know, Ryan wants to add anything to that.
So I think it's a great question. I totally agree. And I think part of it comes down to the classic quote of like, all models are wrong, some models are useful, and we see that here of like, I could have tried to, instead of learning the disturbance, I could have just tried to learn the whole dynamics, but it makes our generative model explode. Like it's way too much to try to learn. It's much better if we can learn this small portion. We don't need necessarily much data. We're relying on our model-based priors. We can constrain what we have to learn. We saw this, or we'll see this in the Lyapunov-based learning constraints that some of the other folks are talking about. And so I think that's really useful. The other thing that I didn't touch on here, but it's buried in some of the papers, is a lot of these are double probability bounds. It's like, based on the data you sampled, can you then enforce this probability bound correctly? Does that data accurately describe your model? So I think there's different things going on here of how much we rely on our models, how much we can leverage that information, and then how much we rely on data. And that's all baked into these kind of guarantees we get at the end. And this is where the stochasticity comes